differential evolution, ant colony optimization, particle swarm optimization. There are many are there. So all these strategies, they have some common points. What are those common points? Like just now we discussed, in a classical search technique, we start with one point, but all these evolutionary strategies start with a number of points that is called search points. So what we will do is we randomly, so going to the example of the surface again, instead of starting at one point here, what we will do in the evolutionary strategy sense, what we will do is we randomly select a number of points. So that will make us what is known as an initial population. So we will evaluate the objective function at all those points. So that's what one important aspect here. So they imitate natural evolution in going from an ordinary solution to the optimum. They are stochastic. They're based on probability in in nature actually. That means because nature also uses trial and error. That means some combination of genes will give rise to a particular offspring, which probably has the best features, so will be able to survive better in nature, etc., etc. So nature actually does this over a period of time slowly by combining various genes available and producing the best offspring, so that the optimum will be reached. So that is what we mean by stochastic in nature. That means it's just a combination of probabilistic combination of various available genetic material. So all of them start with an initial population. So this is the difference between starting with one point and starting with many points initially. So then this population is what is known as the initial generation, and then we will do some sort of manipulations to this population to go to the next generation, etc., etc. So in all these different strategies, these manipulations that are carried out on individual generations, they will differ. So in genetic algorithms, you have certain mathematical operators known as selection or reproduction operation, crossover operation, and then mutation operation. In other methods, the names may differ, but more or less it comes down to the same thing, that if you start with an initial population and you try to find a better solution in the next generation, etc., etc. So you will produce a number of generations and hope that the final generation will have the best optimal solution. So the fitness function value is actually nothing but the objective function if it's a maximization problem. We'll see that in a minimization problem, we'll slightly modify this. And so let us first take a look at genetic algorithms. So they start with the initial population of randomly selected feasible solutions. So now I hope you know what is meant by feasible solutions, because I have shown you what is a feasible region, because all the solutions which can be picked from the feasible region are known as feasible solutions. So it uses the following operators: reproduction or selection, crossover, and mutation. So let's now see, okay, now let us see how we can solve a single objective optimization problem. So now in this case, suppose we have a problem of finding the minimum of this function. Now this function is available to us. So this is a very simple problem. Of course, such simple problems do not require genetic algorithms. We use genetic algorithms to solve really large scale optimization problems, which are actually in computer science known as NP-hard problems. That means they require a really large computer time and effort for the search. So those type of combinatorial optimization problems can be nicely tackled by genetic algorithms. So, but for understanding the progress of the method, we'll use this as an example. So here, suppose our objective is to find the minimum of this objective function. That is, the function is given by here 2 plus 1.5x plus x square. So now we'll see. We'll first select a random points, set of random points. So in this case, now because we have actually seen that our graph has a minimum at the value of 2. So we can normally take this lower limit and this upper limit, that is 1.5 and 2.5, I think 1.4 and 2.4, I think, yes. So these are the lower and upper bounds. Within those two bounds, you can use a random number generator to actually produce a number of points. So these number of points actually will make up the first population. And here, I think we have selected the population size as 10. So these 10 values, for example, 1.78 or 2.004, etc. So all these points are within the lower and upper bounds of the decision variable. There's also this independent variable also is known as a decision variable. In this case, it is x. So x varies from this point to this point. So we have selected a number of points. And each of these points, what we will do is we'll evaluate this function value. So we can plug in the x value here, and we can calculate f of x here. So that is what is known as a function value. So now let us say that by using a random number generator, we have produced these 10 what are known as chromosomes because they give rise to the the objective function here. So here, sorry, I have used a different objective function here, 8. So that also actually, yeah, this also gives rise to a similar graph actually. Okay, fine. So anyway, the objective function is available, only the parameters are different here. So what we can do is we can calculate the function values, and for a maximization problem, the function values themselves can be used as what is known as a fitness function. The fitness function is a measure of the goodness of the objective. That means if the fitness function is more, our objective is better. Our objective is served better. So if the fitness function is less, so the objective is not served that well. So that's the meaning of fitness function. So if you have a maximization problem, then the objective function value itself can be used as a fitness function. But in this case, because our objective is to find the minimum, so our fitness function f of x is actually written as 1 by f of x plus 1. Now this plus 1 is used here just to make sure that when the objective, the function value itself is 0, then you will not have a problem of division by 0. So it will, even if f of x becomes 0, you will still have 1 by 1. So that is just conversion of reciprocal, taking the reciprocal with after adding 1. So this is how we get to this. And then we can calculate all these values for all these different. So these are the initial population values, and these are the function values, and these are the fitness function values, because the fitness function values are calculated as 1 by 1 plus f of x. Then these are calculated, these are the probabilities of the fitness function values. That means what we will calculate as a probability. The probability means if we sum all the objective function, fitness function values, and then take the fraction of that, then we will know which chromosome has a higher fitness function. So that is how we will call this the probabilities. So if the fitness function has a higher value, then the probability will be more. So the probability is more for a better located point as compared to the probability of a point which is far away from the optimum. So then we will calculate the cumulative probabilities. That means the sum of all these probabilities. As you can expect, the total final sum will be equal to 1. So what we will do is now in the first operation here. So what we have is initially 10 members of the population. Each member is having a specific fitness function. But now in the first operator, that is, the mathematical operation that we carry out to go from one generation to the next generation. Remember, this is equivalent to saying starting from a single point to go to the next point. That is if you are starting with a single point in classical optimization techniques. But in evolutionary strategies, as we said, we do not start with a single point, but we start with a population of a number of points. So that is why we call it a first population, initial population. And then we go to the next generation. How do we go to the next generation? We hope to create a better population. That means all the chromosomes in the next generation will have higher fitness function values. So how do we do that? The first operation we do is selection operation. So how do we select? An example of this operation is carried out by what is known as a roulette wheel. Now, this is a wheel which actually plots the probabilities. So higher the probability of a particular chromosome, the larger segment it will occupy. In this case, of course, the segments are looking more or less, close. And so, but you can imagine that if a particular chromosome has a larger segment, that means because its fitness function is more, so if it takes a larger segment of this roulette wheel, when you turn the roulette wheel, the probability of the pointer falling in the larger section will be more. That means you turn, so for the first generation 10 population members, what we will do is to complete the first operator here, the selection operation. What we will do, we'll turn this roulette wheel 10 times. Now, if it is turned once, then the chance of the fitness function having the large value coming into the arrow point for selection is more. So that is how the fitness function, those chromosomes which give rise to larger fitness functions will be repeated more number of times when you turn the wheel 10 times. So in the next 10 population chromosomes that you will have a repetition of more, like for example, in this case, you can see X values selection. So here you can, so because in this particular case, I think this point is repeated 2.229, so 2.229. So this point is repeated. So the 1.49, 1.49. So this is repeated. So those values which have higher fitness function values get repeated. That means you are informing the next 10 members of the next generation, you are eliminating some of the worst performing candidates. So the best performing candidates will get repeated. So what happens is in your at the end of the first operation, selection operation, you'll have more of the better placed points as compared to your earlier listing. But what will happen is there's no point in having redundant points. So what we will do is we'll go to the next operation. That is what is known as a crossover operation. Now we will use what is known as a coding of these. So all these decimal values of our decision variable are actually coded as binary numbers. So this 2.0049, this corresponds to this. Now, of course, the initial span of the decision variable, that means from 1.4 to 2.4 that we selected, that is a distance of 1 actually. Now, on a real number axis, this 1 can be divided into any number of segments. So it depends on how many bits of the binary number that you are selecting. If you, for example, if you select only 4 digits, 4 bits, then you cannot find, you cannot find many portions, or you cannot divide it into many parts. So what we will do is we'll use, in this case, I think we have used 16 bits. So the value from 1.4 to 2.4, the real axis, is divided into as many points as that will come out of this 16-bit binary representation. That will be around 65,535, I think. I have written the number somewhere actually. Okay. So, so that is how, each of these numbers will get converted into an equivalent binary representation. So this value is represented by this, but this is what is now known as the gene. Actually, in this case, of course, there's only one design variable. So each population member will have only this single gene, as well as it also forms the complete chromosome. For example, if your objective function is a function of two variables, two independent variables, x1 and x2, and each of them will be converted into equivalent binary codes, then they will be placed next to each other. So we'll have some binary code for x1, another set of binary 16 digits for x2. So they both together will form what is known as the complete chromosome for that particular point, population member. So, but in this case, the problem is a single variable problem. So you have a gene as well as the chromosome, they're same. Now here, after converting all these things, what we will do is, we will now remember the higher fitness function values are repeated here. So what we will do is, we'll use this next operation that is known as crossover operation to modify these population numbers. So in crossover, what happens is, for example, you have XA, this is one chromosome. Now this is an example chromosome here I have taken here, 110000, 11, etc., etc. Now we have another chromosome, XB here, etc., etc. Hello. You have any questions? Can I proceed? Are you able to hear?
Yes, sir. You can proceed, sir. We are
Okay,
able to
okay.
hear you.
Okay, okay. Do you have any questions? If anybody has a question, please ask me, no problem. Okay, so what we will do is, let us say that we have two chromosomes, XA and XB. Now, what we will do is, we'll use a random number generator to call for a random number, an integer random number between 1 and 16. So that will give us this number of the position of the bit from where we need to do crossover. So for example, in this example, I think I have seen that crossover is done from this bit onward. So the last 4 bits are crossed over. So these two, the members of the initial population are selected for crossover. And once you do the selection, what you do is, you call for a random number which will locate the position from where the crossover has to take place. Now here, suppose from this bit to this bit. So this bit onwards towards the last bit, from this bit onwards towards the last bit. So these two get crossed over. That means this 4-bit segment will come here, this 4-bit segment will go here. So after the crossover operation, this red color chromosome will remain same till this. Okay, the last 4 bits will be taken by these 4 bits. So you can see. So the new chromosome is this. Similarly, the blue chromosome will remain blue till this. And the last 4 will be taken from the last. So I hope you understood. This crossover is clear. So, but this, see, the idea, the most important idea where we are following nature is using probability here. So we are stochastic in nature. That means we are not fixing in advance that for every crossover operation, the last 4 bits will be crossed over. So we are not fixing that. We will call a random number. So this crossing over is also randomly done. So sometimes you will have all the last 6 bits or 7 bits or whatever it is. In fact, this is a very simple example of just using 16 bits. But in a real life large problem, the chromosome itself will be very large. Just imagine if you have, some 300 variables. So just imagine what will be the size of each variable. Again, you are using some 16-bit precision to represent each variable. So 300 into 16. So that will be size of the chromosome. So many ones and zeros will form a big, huge chain. So that chain, so 2 such chains will be paired for possible crossover operation. So once that crossover is done, you'll get two new chains. So these are the two new chains after the crossover operation is done. I hope this is clear. Is that clear? Okay. So what we'll do is now once the crossover is done, so your redundant population members will no more be same. So they will form new members. So the basic idea here in the crossover operation is to actually, what we are doing here is actually you can clearly see the MSBs, most significant bits. That means the bits on the left-hand side are kept as it is. The bits on the right-hand side are crossed over. That means it's actually, it corresponds to a little exploration of the neighborhood. That means some in decimal form, your 1.49445 can become possibly 1.5643 or something like that. So you're in the neighborhood of that point only, but you are exploring a new point like that. So this will be done. But then there is also another operation called the mutation operation. Now, in this mutation operation, what we will do is some gene structure will be mutated because of some unforeseen reason. So that's what happens in nature. So genes get mutated for some, some external factor coming from the environment. So here also what we will do is, once you have done this crossover for all the 10 members of your initial population, you will have 10 members of the new population. But then what you will do is you will use those, you will go to each of these 10 members and call for a random number. And then if that random number happens to be less than or equal to what is known as a mutation probability of mutation, then you will say that, okay, this particular number will go through mutation. And then you will call for another random number, which is going to be an integer number. And that will give rise to a particular location of the bit, which will be, so in mutation operation, I'll take this as an example. Suppose we are looking at this particular chromosome and say that, okay, this chromosome will call for a random number, and then the random number probability value, the value of that random number will be less than the probability of less than or equal to probability of mutation. So that means this will be selected for mutation. If it is more than that, it will not be selected. You'll go to the next one. Or if it is selected, then you will call for another random number that will tell you which of these bits will be mutated. So suppose that integer random number happens to be this bit. So what happens in mutation is basically you make this 1 into 0, or if it were 0, you convert it into 1, like that. A simple change. So 1 to 0 or 0 to 1. So that is what is mutation. So this mutation actually introduces subtle changes in the existing population members. So just to ensure that you don't lose information in the set space permanently. It's because if mutation is introduced with a small probability, then it gives rise to some explorations in such a way that new regions of the set space can be explored. So this is how the genetic algorithms are used. So from one generation of population to the next generation of population, what you do is you do crossover, you do selection or reproduction, then do crossover, then mutation, so that a new generation of the population will be generated. Once again, you evaluate the fitness function for each of these members of the population. Then once again, you continue like that. Then you continue over a fixed number of generations or till convergence is reached. That is genetic algorithms. And personally, I have very good experience in using genetic because we have solved many problems from various other fields also, like multiprocessors in computers. When you have many processors where a lot of jobs are coming in, and then some job has to be processed in reference to the other jobs, etc. So the scheduling of jobs. which is very similar to scheduling problems in chemical engineering. So all these problems, actually real life problems, have been tackled easily with general algorithms. I'll also show you another example also. But first, let us see another example of an evolutionary strategy, what is known as a differential evolution. So here also we will start with a set of population members. So in this case, you can see that each population member or chromosome, it consists of X and N number of decision variables like your temperature, pressure, composition, etc. So for a particular problem, you may have a large number of variables. So all the variables values within the limits, lower and upper bound limits, are actually taken randomly to formulate the initial set of population. So you have XNP is the number of population is NP. So many, like in the example that we have taken there were 10 population members, but 10 is a very small number. Normally we use 100 or something like that. So if you take 100, you'll have to create 100 vectors like this. So that is one important thing. So all individual vectors are created in this fashion. So this is this is xi or any of these x1, x2, etc. This is equal to li. That is the lower limit on the ith decision variable plus random number between 0 and 1. That is a random number generator. It multiplies the difference between the upper limit and the lower limit, and then it adds to the lower limit. That's how the one value of one decision variable is calculated. This is repeated for all the decision variables, n number of decision variables. Put them together, you will get this one vector. So this has to be repeated np times. So after you create all this np number of population members, then you go through the similar set of operations. So these are the things that you need to provide initially: the number of populations, scale factor, and number of generations, etc. You also need one more, actually, another probability value. Let us see. So for example, if you have two, x1, x2, so you will have you can create values like this. What we will do is, let us see. So the initial population, creation of initial population is more or less similar in both genetic algorithms and differential evolution. But what happens in differential evolution is, after the initial population is created, what we will do is we'll create what are known as a trial vectors. So this trial vector xt is a combination of three randomly selected vectors. So first is what is known as a base vector. Remember, but all three are selected, picked from the initial population only, but randomly picked. Okay, so XA is picked, then XB and XC are also picked, but their difference is actually multiplied by what is known as this scale factor, and then that is added to this randomly picked vector, and this whole combination is what is known as a trial vector. So this is how we create trial vectors. So if you are starting with 10 population members, you'll have to create such 10 trial vectors by using this randomly picked vector combination. So this f is normally less than or equal to, it is between 0 and 1. It's also known as it controls the rate of evolution of this population. So once this is done, the other operation is a very similar operation, what is known as a crossover. In this case, what we will do is, for the trial vector, we will look at individual decision variables. So this UI, so this X vector has a set of decision variables, x1, x2, etc., small, represented by small letters. So those things are individually altered between the trial vector and the population vectors. So you swap the decision. So if you select two vectors, one is a trial vector or mutant vector that you created from the first operation, that is mutation in differential evolution, and you randomly pick up a member from the population, existing current population, and then what you do is you compare those two, and then you compare those two from the point of view of individual decision variables. That means in this case here. So suppose you have randomly picked 3 vectors from here and you created a trial vector. So your xt is this. Now you have randomly called for another member of the population. So what you do is you compare these two. So this decision variable is compared with this decision variable. This decision variable is compared with this, etc., etc. So once again, what you do is after you decide to use these two vectors, randomly selected vectors, one from the trial vector set and one from your old population or current population. Then what you do is you compare individual decision variables and then you swap some of them, okay, so that you will get a new trial vector. So that is how your trial vector set is modified in the crossover uh, process. So once this crossover process is done, uh, and the first is mutation, then the crossover process is done. Then what you do is you take, so now you have a set of, members, say for example, 10 members of the current population, and you have created 10 members of the trial solutions by using these two operations, mutation operation and crossover operation. So now you compare each one, the first member of the current population with the first member of the trial vector, and then you see which one is providing a better fitness function. So if it is providing, if the trial vector is providing a better fitness function, then you replace your original population member with this trial vector. So it becomes the population member for the next generation. That is what you do for each and every one of the population members. So that is how your differential evolution creates a new generation. Once again, the complete in the process or operators are repeated: mutation, crossover, and selection. So those are the 3 operators in differential evolution. So these are the 2 examples which I have personally used in many problems. So that's why I explained. But there are a large number of evolutionary strategies. In fact, there is a website known as Nature Inspired Optimization (NIO). In fact, they conduct annual, conferences every year. So if you go to their website, you'll find that there are a large number of, for example, ant colony optimization, for example, firefly optimization, for example, particle swarm optimization, water droplet optimization, gravity optimization. So a number of optimization techniques based on evolutionary strategies is very large. Okay. So in fact, this example I'll just tell you. This is one example of the D. This is what is known as a test function. There's a Rosenbrock function. So to find the minimum here, so what we do is I'll show you one instance of running. These are the contours of this function, and one instance of running this D will show you that this is the optimum, and this is how the D progress has been shown here. So it starts at some initial point. These points are actually because you say, okay, in one generation you have 10 points. So which point are we plotting here? The best point available is what is plotted here. So the best point in one generation is this. Next it goes to this, like that, it progresses, and it comes to this. So it comes close enough to this. So this is what we can see. So these problems, of course, are very simple. We don't need GA or DE for these problems. So what we'll do is we'll take a realistic. This is a real practical industrial example that we have taken here. This is an ammonia synthesis process. This is an ammonia reactor. So in this ammonia reactor, the syn gas, that is hydrogen plus nitrogen, are reacted together. So this is your reactor here. So the feed gas is passed from here. So it will enter through the top here. It will enter through the top here, and it will enter through the top here. And then it comes across this catalyst bed. So the bed is actually divided into 4 sections. The first segment is this section, is this, second, third, fourth. So after it passes through the first section, because the reaction is synthesis reaction is highly exothermic, it gets heated up. So what happens is it's not good for the progress of the reaction. So what we will do is we will not pass the entire feed, all the feed directly at the top. We'll divide this into a smaller branches here. So three, we'll call this the quench streams. So we'll send one stream here at the end of the first section of the bed. We'll send the second stream here at the end of the second section of the bed, and third at the end of the third section of the bed. Okay, so now the feed stream, because it's at a lower temperature, is partly used here to cool the gases coming out of the first section of the catalyst bed, because they have already, the reaction has been carried out in the first section, so they become hot. So what you do is you introduce a part of the fresh feed, which is at a lower temperature, to cool it a little bit, so that the reaction in the next section will proceed smoothly. Then again here, this new second quench stream is coming. Again here, the third quench stream. So these three quench streams, the flow rates of these three quench streams is what we need to optimize, so that the conversion is maximum amount of ammonia is produced. That's what. So if it is not quenched, then the reaction rate will be affected. You will not get the maximum conversion. So this is a problem. So what we will do is, so these are the reactions. So this is your objective function. Maximize F, that is equal to the final product flow rate into the mole fraction of ammonia. This is what we need to maximize. And then the mass balance equations are given by these differential equations. The energy balance is given by this differential equation across each bed. So we need to calculate, what we need to do is we need to solve these differential equations by some numerical methods. So we'll assume some starting values. These are the values given here: the temperature, the dimensions, the initial mole fractions, etc. And then we'll start with some assumed values of the flow rates here: gas flow to the first bed, second bed, etc. Then all of this is fed to the model equations, that is the mass and energy balance equations. So they are solved so that we can finally get the output product value. Then we can calculate what is the fitness function, that is how much of ammonia is produced. So this is what happens. So for each set of values of these parameters, we need to simulate the entire reactor operation so that we can finally get a fitness function value. So this is what is done here. And if your population has, say, 10, 20, etc. Remember, in this case, the objective function is consisting of three variables here, because the three variables are the three mass flow rates of the quench flows. So here, this is Q1, Q2, Q3. So these are the three mass flow rates of the quench fluids, which are the variables here. So what will be the final production of ammonia will depend on how you are dividing the initial Q0, that is the feed flow rate, into Q1, Q2, Q3, etc. So this is how you will pass these three values of these three variables into the simulation model. Then this whole reactor is simulated, and finally your output is calculated. That gives you one objective function or fitness function value. So that is how. So if you have 10 members in the initial population, you'll have to do this operation 10 times so that you'll get 10 fitness function values. Like that, we used genetic algorithms. So here is the flow sheet for this. This is the crossover mutation, and also we used some technique known as elitism, that is in maintaining the best member in a population securely. That is what is known as here. So that's how new generation is. So initial population is sent to the simulation model here. So that the initial population means what? Sets of three values for the three quench flows. They will make up the initial population. They will be sent here. They will go through this entire simulation algorithm, bed 1, bed 2, etc. After solving all the equations for all these beds, then you will get this final values. Then you'll get the fitness function, and from here we'll do this crossover mutation and etc. And then create new generation, like that it goes again. So this is repeated a number of times, large number of times, so that we will get the final. So this is a realistic problem, very large problem, and this requires the, algorithms like genetic algorithms. So we use that and we solved it. So these are the initial profiles of, this is the initial profile of mole fraction of ammonia. At the end of the first bed, the mole fraction will fall down suddenly because you are feeding the quench stream, the feed stream again, which contains less of ammonia. So it will fall down. Again, through the second bed, it will go rise because reaction has taken place. Again, it will fall down, third bed, and finally fourth bed, like that. So these are the, you know, and this is how the temperature variation also occurs. Temperature rises, then it will fall because the first quench stream has entered, so it will cool down. Second bed, it will again fall, like that, it will rise, again fall, like that. So these are the non-optimal values. And finally, we have found out, after using genetic algorithms, we found out the optimal values, and these are the results. So the best value for ammonia production is achieved at these values of syngas distribution in the reactor. The maximum production achieved is 1764.53 kilomole per hour. This comes out to something like finally 4.4%, an increase of 4.4% in production for 700 tons per day ammonia and planet. So this is what we achieved by using genetic algorithms. So these are the optimized flow rates. So this is the temperature profile, and this is a mole fraction, right? Okay, so this is a comparison. So that is one large scale problem that we have tackled using GA. The other problem is a semi-batch reactor. Here in this case, a batch reaction, actually it initially starts with one component. The other component is fed as a fresh feed at a particular flow rate. So basically what happens is the flow rate is to be sent in as a function of time. So if the semi-batch operation is taking place over, say, a batch time of 2 hours, so over a period of 2 hours, how will you decide what is to be the feed flow rate of this second component into the batch reactor? Because the flow rate, which is actually, which is a, this actually is a very difficult optimization problem from a conventional point of view, because unlike a simple function optimization problem, this actually gives rise to a very difficult problem, because here you are not finding out only a peak point or a trough point on a surface. Here you are actually trying to find out the entire surface itself. Which type of surface is going to give you the best results? So that is the problem here. So this problem, tackling this problem using conventional means is really difficult, because this requires a completely what is known as a different set of techniques known as calculus of variations. Mathematically also is very difficult, and calculus of variations works well only if your functions are nicely behaving mathematical simple functions. But in practical life, for example, if you are trying to find out, say, the optimal path for a spacecraft to leave Earth and reach Moon, so that will be a very highly nonlinear path, which has to be found out using calculus of variations. So that is also another example. So in chemical engineering, this batch reactor operation is another example. So these are very dynamic optimization problems. They are difficult to solve. So what we will do is we'll see how this genetic algorithms have given rise to. So I have not given the details of this, but I'll show you the exact thing. What we have done is, see, the time of operation is divided into small values, so small segments. I think it is 10-minute segments or something like that we have taken. So so for each period, or each 10-minute small time period, what we have done is we have assumed a constant feed rate, and then this whole thing is created as a profile. So that means what? So if the total time is 5 hours, so you can imagine, I think it is 10 minutes or something. I forgot actually. So So there's so many segments out there. So for each segment, you need one variable. So that means there are so many variables here. Um, 20 or 25 variables are there, I think. So 20 or 25 variables. So for each segment, you'll have to assume some flow rate here. So that combination of all these segments will give you one profile. So this one profile will be fed into the reactor, and the reactor reactions are simulated to give you the product. So that gives you one fitness function. So again, you'll have to find out, you'll have to use another profile. So this is what I mean. So here in this problem, we are not trying to find out a fixed point. We are trying to find out the optimum profile. So for each profile, there are a large number of segments that combine together. So all these segments will make up the chromosome for your genetic algorithms. And so many chromosomes will have to be used in the initial population. So this whole thing, this is also a very difficult problem, but it has been made practically feasible by genetic algorithms. So we solved this problem also. And so another problem that is a large scale problem is also cracking of hydrocarbons. So here it's a tubular reactor problem. This was a 95-meter tubular reactor. Then the initial specifications are temperature profile and outlet composition. Here in this problem, actually the problem was to find out the optimum parameters for the reaction rates. So in this cracking operation, a number of reactions take place. So like this, a large number of reactions take place. In all these reactions, you can write down the reaction rate constants, rates of reaction as this. Right? In the rate constant, you have this rate constant values. So these are to be optimized. So what we had was a set of available data, the output compositions, with specific input data. So for each specific input data, you get a particular, it's as if you are passing through the initial values into the reactor, simulating the reactor, the tubular reactor, and then finally you will get the output. So the output composition, what you get for a particular set of inputs, has to be compared with available practically conducted experimental data so that the difference can be minimized and you can find out the optimum set of values here. So actually, one set of values for the variables consists of 22 values for K naught and 22 values for the activation energy E. So there are 42 variables here. So in this case, the 42 variables will form the decision variables. So that means your one chromosome will have 42 X1, X2, etc., etc. So these, like that, you will have to make a large set of populations, and then we'll have to feed that into the reactor model, and then we'll have to find out the minimum of this sum of, that is a least squares problem. So this we solved using both GA as well as what is known as a nonlinear simplex method. This is a nonlinear deterministic method. So these two methods were used. Now there are many other examples that I have not shown here, like for example, finding the best optimal scheduling on a Mahindra and Mahindra's automobile manufacturing process, which is similar to the pharmaceutical unit scheduling problem also. And other problems, multiprocessor scheduling, again, a scheduling problem. So like that, many other examples have been taken. Large scale problems, all of them, we were able to tackle all these problems using genetic algorithms and differential evolutions, and they work very well on large scale problems. But the other thing is, with this 25 years of experience in solving these optimization problems, especially after coming across these evolutionary strategies, I have, I started looking at it from a slightly different point of view. For example, in nature also, you'll find that nature has been optimized. The evolutionary strategies, when you go to that website, nature inspired optimization, you'll find that there are lots of optimization techniques like firefly optimization, ant colony optimization, etc. So you'll find that everything in nature seems to be doing this optimization. Every creature, in fact, look at you look at the natural creations here. For example, this polar bear. The size of the polar bear is an optimum. Actually, it cannot be bigger than this, or it cannot be smaller than that. So that's because of the need for retaining enough heat in that cold climate, and at the same time, similarly for the shark. So it has to be hydrodynamically, the surface has to be hydrodynamically designed so that the minimum shear stress will be there. Similarly for the bird, in fact, there is a complete PhD thesis available online for the structure of this bird wing. This was done in UK actually. So nature seems to have done a lot of optimization. Everything seems to have become an optimized version. So this has given me a lot of thinking, and finally I realized that if nature has already done the optimization, okay, on this actually many philosophers and physicists also have expressed this. For example, um, this Leonardo da Vinci, this is a medieval artist and inventor, is made this comment: human subtlety will never devise an invention more simple and beautiful than nature. That is Leonardo da Vinci. And the great Leonard Euler: every physical principle can be obtained as a solution to an optimization problem. And so these are the examples. So everything in nature seems to have been an optimized, result. So already what we have done, what we have is an optimum. If what we have is an optimum biosphere, what we are doing is actually a little, we are going away from the optimum. We are not utilizing natural resources in an optimum. Today we are talking about sustainable development, but we are not really doing sustainable development. So these things will be very important for the coming generations. So think about it. But nature inspires, in this field of optimization. And if you have questions, please ask. Otherwise, I hope you have enjoyed this talk. Thank you very much.
Thank you, Professor V. Ramesh. It was a very
Yes.
inspiring talk where you explained nature-inspired algorithms like genetic algorithm, differential evolution to find optimal designs or operating for conditions for complex processes, and can be successfully applied in carrying out optimization with chemical engineering equipments. Now, I would request the audience to ask if they have any kind of queries or questions, please.
Any questions?
Any questions, please?
If you have any question, you can post in the chat box.
Please ask.
I will convey. If any question, you can post box in the chat or question, and I will post to sir.
Or if you have questions later on also, you can mail them to me. Yeah, or you can pass them on to your convener, and
Yeah.
I request the convener to pass the questions. I'm available to answer the questions if you find. I hope you find it interesting. That is my whole purpose actually.
Okay, sir. I will pass the question.
Okay.
Okay.
Thank you. Thank you, Professor V. Ramesh, for this very insightful presentation. I'm sure we all appreciate you for spending these last 2 hours and sharing your knowledge with us. We thank all from the behalf of faculty members of Thadumal, Sani. I thank you a lot. Thank you very much.
Thank you.
Thank you. Thank you, sir.
Okay.
Thank you.
Bye.
Thank
Yeah.
you. We'll meet now at 2:30.
Yes,
Thank
yes.
you.
So our next session at the 2:30 we'll meet at 2:30 will start. So join before the 10 minutes. Okay.